Welcome you. Hello all, I'd like to welcome you all to our third session in PIPESIM Fundamentals. The past two sessions, the first session we spoke about PIPESIM fundamentals in general, talking about both the walls and the networks with an overview about the software and its capabilities. Last session we focused on walls. We spoke about nodal analysis and we opened a PIPESIM user interface focusing on wells, and we built a model together. We ran nodal analysis, and we also added a pump. So if you didn't see the previous two sessions, I recommend that you do so. Today we are going to talk about PIPESIM focusing on network modeling and optimization. Before I start, we all know that in any production or injection system, we need to take care about the wells individually. We need to optimize the well conditions, look into what are the production parameters that will maintain production for a long time. How can we model an artificial lift? How can we model if we want to drill a horizontal completion? And when the well is going to die, like for example, at what water cut, at what reservoir pressure, at what, let's say, wellhead pressure and so on, the well will cease to flow. And all these are what we call, a sensitivity analysis that we can perform in a well. Now, as you know, the wells, when they produce in most fields around the world, the oil or the gas will be transported via pipelines. These pipelines can be complex. They can be connected together, and they will basically propagate into or the production will be accumulated and it will pass through trunk lines, flow lines until it reaches the production facilities such as the separators and so on. It's really important that we take care about the pipeline networks. And the reason for that is with time, pipeline networks can be blocked due to a solid precipitation. If the fluid flow in the pipeline is low, then there could be what we call segregation of the phases, where the water will start to flow at the bottom of the pipeline. And of course, it's not really pure water, it is brine. It's basically water with salts. Sometimes it's acidic, so it can corrode the bottom of the pipeline, which is a major problem in pipeline assets around the world. So if the fluid velocity is very low, we will have corrosion at some time. If the fluid velocity is very high, we will have erosion due to the mechanical effects, especially if we start having sand, etc. So and also it could be that your pipeline network is not optimized, meaning using the same wells, using the same well strength. Okay. If you have, for example, 50 or 100 wells, okay, in your network, by doing some changes into your production facilities or into your choke settings or into the artificial lift quantities you distribute on the wells, you may increase your production. And this is due to the fact that when wells are sharing the same trunk lines, the pressure in the system will propagate into all the wells. And if you don't take care about how to manage your production from your different wells, you will end up having strong wells dominating the production, and the weak wells cannot contribute. And that's why you will need to optimize your production network. And this is one of the topics that we are going to talk about today. So PIPESIM network modeling and optimization. This is the agenda of the presentation today, but let's talk about production system challenges. Okay, we have a production system, all right? This is an example of you know, a gas lift, the gas lifted field. So these are the producing wells. As you can see here, we have 3 wells here, right? The production is going to the right side. So this is the oil or water, liquid. And then we have, so this is the cross section of the well, right? So we have what we call the production manifold. So these are flow lines, and then we have production manifold, all right? And then we go to the separation. We go to the separator, oil and gas, gas and oil separator. Then the separated water will go to the water treatment facility. It can go to the water injection or water disposal well, and the oil will go to the oil storage for the export line. And then the gas could be either also used, exported, sometimes back injected to the reservoir, or in this scenario here, we are using the produced gas, okay, in injection, in gas injection. As a matter of fact, you know, in this schematic also, we do have gas export line. So we are using, you know, this is a compressor, and then we are using some of the gas to be re-injected, okay, into the same well to use it as gas lift injection, okay? So this is a schematic of a production system. But now talking about pipeline networks and large networks, what are the challenges that a producer or, you know, a national oil company, an operator can face? So we have a problem of high operating costs of artificial lift wells. Sometimes if you are using, you know, electric submersible pump or PCP, then you really need a high power, and because these wells can be very deep, and then you need a lot of power for each well. So it's cost, okay? If you're using, for example, in this system here, if you're using gas lift, then instead of actually going and exporting the gas, using it for energy, you're actually re-injecting it to use it in the production. So this is additional cost, okay? So cost these days is very important. And looking into just the cost that will be consumed in artificial lift by itself, it's not really a small number. It's huge. We have loss of production due to insufficient or imbalanced artificial lift resources. So sometimes you have, let's say, in this case here, you have a gas lift system, but then the injection gas, so you are controlling how much gas goes to each well using the chokes, right? Sometimes the gas injection rate is not enough for certain wells. Sometimes we are over injecting it in other wells. And sometimes, you know, we have limited gas lift rate. And then how do I distribute this gas lift rate among the wells? What are the rules? What are the, you know, the controls or the constraints that I need to consider when I distribute my gas lift rates among the wells? This is an important question. And if you have, let's say, 100 wells, 200 wells, then the problem becomes really complex because you have faraway wells, we have wells, you know, connected to for example, production manifolds, and then 2 or 3 wells in the same production manifold is strong, 2 are weak, and so on. So it's really, really difficult if you need to make this right. And that's why you need an algorithm. You need a mathematical solver for you to help you in determining how you distribute the artificial lift quantity. We have a problem of high pressure wells domination. This is a known problem, especially if you have a mature field and then you are drilling new wells. New wells will be stronger, okay? And then when the production comes to the surface, the hydrocarbon will come with high pressure, and then this pressure will propagate to the production network, and then it can cause back pressure to other wells. then this is what we call the high pressure wells domination. The strong wells will be producing, the weak wells will start to die. We have also the challenge of facilities capacity. Like for example, each, let's say, separator at one day I can handle, let's say, certain amount of water, certain amount of gas, right? I cannot separate more. And that's why, you know, I need to control my production in a way that I don't reach my you know, separator capacity. In certain fields where they have only gas cap, for example, if the production becomes high, they have to flare the gas, burn it, okay? Which is of course, you know, a big loss. So you need really to control your production in a way that I don't exceed or don't reach my facilities capacity, which is our separator capacity. We have the problem of the integrity of the assets, corrosion, erosion, scaling, etc. Okay, so as you can see here, there are a lot of challenges in any production system. So it's now we're not talking about the individual wells. We're talking about the whole system, the whole production network. Okay, so that's why you will need to manage your facilities, your field, with constraints. Constraints are limitations, are, you know, conditions that you need your network to be produced with, so that, and at the same time, you need to maximize your hydrocarbon production, right? So for example, you need to not to exceed drawdown limits, because in certain reservoirs, if the drawdown becomes a bit higher than, let's say, maybe 100 PSI, 200 PSI, 300 PSI, then this will affect the integrity of the formation itself. There will be a lot of pressure drop, there will be a lot of turbulence, and then you will start producing sand, and then this is a major problem. You need to look into the shared common manifolds, and this is one of the examples I showed before. Okay, let's say the manifold itself can handle certain production flow rate. So you don't want to exceed that. You have the erosional velocity. If the production is very high and the pipeline is not big enough, all right, I will start having erosion in my pipeline, which is a major problem. Gas processing capacity or water handling, water injection limitations. So this is what we call the facilities capacities. Limited lift gas rate, limited pumping power. So all these are constraints that I need to consider when I operate my field, okay? And that's why we need what we call the network optimization. Network optimization is a big challenge. And there are different scenarios that any operator can let's say, select from, or it could be a combination of all. Let's say, for example, an operator needs to maximize production at the lowest cost. So this is the optimization goal. This is the optimization scenario for the operator. For example, one of them, to maximize production at the lowest cost. So you will need, for example, to avoid excessive gas lift injection. You don't want to inject too more, right? You need to reduce ESP or PCP power consumption while maximizing oil production. So this is straightforward and logical example of maximizing production at lowest cost. Another operator would need to focus on the major problem is the limitation in the facilities they have. Like, for example, they want to only, so it's not really about cost, it's to honor the facilities handling capacity. Like they need to control the total water production or control the total gas production. They want to limit, the total production of water. They don't want to produce, let's say, at 30,000 barrels of water, more than that. But at the same time, they need to make all the wells contribute and maximize oil production. How can they do that? Some operators, they need to increase reservoir recovery. This is their main objective. Okay, it's not really about how to maximize oil production. There are many national oil companies they can open the tabs. They can literally open all the chokes and produce. That's I mean, let's, for example, Saudi Arabia. Saudi Arabia, they have excess capacity of more than 2 million barrels per day. More than that, okay? So they are able to actually open the tabs and then produce an additional 2+ million barrels per day. But they, they and other operators, their objective is to increase the reservoir recovery instead of maximizing production. What do we mean by that? If you have a well, this well, if you produce it at, let's say, 3,000 barrels per day, okay, it will produce, but then after, let's say, 6 months, 1 year, 2 years, you will start inviting water because the drawdown is high, okay? And then once the water comes, once the water reaches your completion, then your recovery will drop because the mobility of water is much higher than mobility of oil, and then the water will start coming to your reservoir, to your well, and then the oil cannot flow because it's competing with water. Okay, and that's why you need to maintain, instead of producing, let's say, 3,000 for 2 years, I can produce 2,000 for maybe 5 years, which is more cumulative production. I can increase my reservoir recovery. So that's why the operator needs to avoid excessive drawdown, control high water rate per well, or sometimes we can do the optimization on an individual well that has multilateral. And if you have multilateral, you need to know what is the right combination of flow control valves. Like, for example, if I have 3 or 4 laterals in the same well, I need to know what is the optimum, what is the best way to open the downhole control valves, okay? Finally, maintaining asset integrity. Many clients, their main objective is actually to avoid erosion and velocity, avoid excessive H2S production, operate ESPs and PCBs with acceptable operating envelope, okay? And it could be that an operator can have, all these scenarios together, all these production optimization scenarios together. And that's why you need a powerful network simulation software and optimize it with an optimization algorithm that will help you, maintain all these or work under all these scenarios, okay? So pipeline network modeling in PIPESIM. PIPESIM is considered one of the standard software for one of the industry standard software for network modeling in the market today, okay? It has unique network modeling capabilities, such as it has both the logical network canvas. So this is what we call the logical network canvas, all right? In which basically you see the wells connected into junctions and then the pipelines. Or you have the GIS, GIS, which is Graphical Information System Network Canvas. So this is another display of the network, okay? And you can switch back and forth between the two canvases, all right? And in the GIS network canvas, you can look into the well locations, you can look into the results gradient, etc. You can have automatic network model building using the GIS shape files. So when I am in the GIS canvas, I can import what I call shape file. The shape file is nothing but a 2D representation of this flow line, okay? That is normally generated by, the mapping services in any company. So in any company, if they want to, they usually have a GIS or mapping services or mapping unit or a division to do mapping for all their flow lines, trunk lines, pipelines, etc. Okay, and these pipelines usually are composed or are saved as what they call shape files. It's a layer of basically lines and connections when it has information of the pipeline networks. If you have the shape file, it is .shp. Okay, SHP stands for the shape file. If you have the pipeline shapefile in your company, you can easily import that into PIPESIM and you can build your pipeline network automatically. And I will demonstrate this today. You can also build your network automatically using Python scripting. All right. If you have the data stored in Excel or in any other means, any database, you can develop a pipeline, a Python script to automatically build your wells and network models, build all the connections, even run the simulation without opening the user interface. All that can be done using Python scripting. And we have integrated wells and pipeline networks in a single model. Okay. Many available other software in the market, you will need to model the wells in a separate software, save it in a separate file, and then model the network in another software, and then import the data for the wells, okay, for each well from the other software. And then you need to generate what is called, VLP, vertical lift performance, or outflow curves, to model the wells. In PIPESIM, we have integrated wells and network models, okay, in the same file. And the file is not big in terms of size, okay? So you can easily double-click on a well icon, and then you will open the well data. You can change the well data. You can even run the simulation for that well while you are in the same network model, okay? And then we have a separate production optimization service. What we have is that we have the network simulation, which is the model itself with all its configurations based on the current operational data. And then you can run an optimization service on top of that. This optimization service, while it's running, it will show you, it will give you the recommendation for new field settings, such as the choke settings, distribution of artificial lift, etc., and without touching the network simulation itself. And then if you are happy with the recommendations that the optimizer will give you, you can then send these recommendations back to the network simulation model. So talking more about the network optimizer in PIPESIM. PIPESIM Network Optimizer also has unique capabilities. Number one, we have what we call accurate and smart well curve generation. Maybe this is a bit of advanced to most of the audience here, but let me just quickly describe what we're talking about here. For the network optimization, in order for the simulator to find the optimum settings, it actually needs to run maybe 50, 60, or maybe 100 network simulation settings to find the optimum. And for that, it generates what we call well curves. So the well curves are basically predefined conditions, or oil production versus, let's say, choke size. So the simulator, before running the optimization, will go and create this curve for this well. And then when it runs the network optimization, it will start, just playing with these well curves until it finds the optimum combinations. And then when you publish these new settings, the new choke size into the network, then you are going to run the network simulation again completely from the sand phase. We can have runtime choke bean size calculation. So this is what I just showed you. So it tells you the required or the optimum choke bean size, right? The recommended choke bean size in order for you to maximize oil, maximize gas, or honor your constraints, for example, okay? And then you can publish back to the network simulation. You can honor total system gas lift rate and or total system power for ESP and PCP. You can specify what is the total artificial lift quantity, and then it will distribute the quantity among the wells. You have the concept of optimization studies. You can modify boundary conditions and phase ratios for testing different scenarios. And then this is what I mentioned many times, review and publish the optimization results to the operational network automatically by clicking on publish optimization results back. We have 4 well control optimization variables. So the optimizer can tell you what is the recommended choke bean size automatically. It can tell you the recommended gas lift rate automatically, all right? The ESP frequency and the PCP speed. So suppose that you have, for example, 50 or 60 wells, and these wells are operated using gas lift. Okay, so each well is modeled separately, and then let's say each well has, for example, 1.5 million standard cubic feet of injected gas. Another well has 2, another well has 0.5, etc. Okay, but then you need to optimize your production. You need to maximize your production and reduce your distributed gas lift rate. So you go to the optimizer and run it with the constraints. You put constraints. You say, okay, I want to maximize liquid rate. This is my maximum gas injection rate that I have. Show me how do I distribute the gas lift rate among the wells. So the optimizer will run. It will give you new recommended gas lift rate for each well. And then you can, with a push of button, you can send these gas lift rates to the wells. And then you can run your optimized case in the network. These are the constraints. So we can define, for example, min or maximum Q liquid or liquid rate for the wells. We can put the maximum liquid rate on flow lines, sinks, global constraints, etc. Maximum GOR, maximum erosion and velocity ratio, maximum CO2 and H2S on the pipelines, etc. Or globally on the whole field. So let me just show you the workflow, how we run the network optimization, and then I will show you a demo later on. So number one, we can review the boundary conditions. So when I have a network, okay, I will start, and now I have launched my network optimization, okay? I will review my current boundary conditions. The boundary conditions will tell you, okay, what is the current reservoir pressure for all the wells, okay? What is the, if I have defined flow rate, what are the temperatures, etc. Okay, and then if I'm happy with that, I can of course change these boundary conditions if I want, and then I can review or modify the initial conditions. So these are the initial conditions, for example, currently in the field, the injection gas rate for injection wells, for gas lift injection wells, the ESP frequency for the wells, you know, if I have choke sizes, etc. Okay, and then I can also, you know, change these initial conditions, and I can also change the control type. So, for example, if a well has, let's say in this case, for example, this well has gas lift rate, has ESP, and also has you know, a choke size, then I can select one of them. All right. Of course, this is very weird example, but we just did it for the sake of benchmarking. But I can select, for example, the choke only to control the production. Okay. Then you can set the local constraints. So, for example, these are the ESP lifted wells. So I can define the local constraints. Minimum power, minimum frequency, maximum frequency, minimum liquid rate, maximum liquid rate, etc. So all these are for the wells, okay? And I can select one well, I can define my own, let's say, local constraint, okay? I have, for example, maximum drawdown, for example. I can define what is my maximum drawdown per well. I can set the optimization control, such as, you know, the fixed injection gas rate, fixed power. This is my objective function. Like, for example, I need to maximize oil rate. And I can put a global constraint. I can say that, okay, my maximum water rate is, say, for example, 10,000 barrels per day. Okay. Then the optimizer will run, and then it will honor these constraints, and then it will start to distribute the artificial lift quantities. Then this is the some of the optimization options. And then I run the optimizer engine, I see the progress, and then I can validate the results. So now these are the results. As you can see here, for the gas lifted wells, I have now the new gas lift rate. These are the optimized ones, okay? I can review, I can see that, for example, this is the total oil rate. There's a reduction in oil rate because I put, for example, constraints. This is the total water rate, etc. And then if I'm happy with this, I can basically publish optimization results back to the network. And then these controls will be sent back to my production network. Let me show you a case study. Okay. This is a big network. Okay, huge network of one of the operators. It has more than 500 oil wells. This network is naturally flowing. All right, there is no artificial lift. Very strong reservoir. It's choke controlled. Okay, so all the wells are controlled by the surface choke. The free flow capacity, this big field is producing 2.65 million standard barrels per day. Okay, oil. It's also producing 900,000 barrels of water, and it's producing 2.5 million standard cubic feet per day. So this is the overall production, what we call the free flow capacity. This is if we don't, control any well. If we flow all the wells with its maximum capacity. The well performance is ranging between 1,100 to 11,000. As you can see, there is a big range. And the drawdown is also, ranging between 116 and 880 PSI. Okay, this is also a big range, right? So now we need to optimize this field. All right. What are our objective? The optimization is the optimization scenario. I need to maximize oil production, but I need to cut the water production by 30%. I need to produce not more than 600,000 barrels, although the free flow is producing 900,000. Okay, so now how would the optimizer do that? Well, it will, because it knows the water cut, it will go to the wells with high water cut, and then it will choke them back. All right, in order for it to reach my maximum, let's say avoid, not to how can I say that? Just to obey the global constraint of maximum water rate. Okay, and then there is also a local constraint on all the wells that the maximum drawdown should not exceed 400 PSI. As you can see here, I have wells that are going to more than 800 PSI of drawdown. Of course, the expectation when I do these, all right, of course, I will get lower oil production. I'm expecting that because I am actually, my objective is to cut water production. And of course, no matter how I need to maximize my oil production, of course, the only way to do that is also to cut the liquid rate in general. And that's why I will expect to, have less oil production, but of course, not at the same rate as the water production. So we use PIPESIM to do that. And then in the beginning, the well curve generation took 70 minutes. Of course, this is normal because generating well curves, you do it once, okay? Because you are now replacing the well performance with well curves in order for the optimizer to run. And then the optimization took 2 minutes only. Then the results, the optimization succeeded. As you can see here, this is the total water rate. It is less than 600,000, okay? This is the drawdown. As you can see here, it is not more than 400. And now I have the new bean sizes, the new choke sizes. And now you will see that, for each well, I have now automatically identified the choke size, okay? Now I can publish these optimization results back, and I'll have an optimized network, okay? So that's it. I think this is the end of my presentation. I will go now to showing you a demo. Unless you have a quick question, we can do that. Okay, so let's go to the demo then. Nikhil, I think it's better if I rejoin because my machine is becoming heavy again. So can I do that quickly? So before going to the network optimization, let me show you an overview about the network production simulation, okay? So as I said before, we have the network schematic, right? In this network schematic, you can actually see the logical diagram. Like for example, you can double click here and then you can look into the pipeline data. We have the inside diameter, and this is the horizontal distance, the measured distance, the latitude, the longitude, and the elevation. The reason we have latitude and longitude is because this was populated from the GIS map, okay? Now, this is well number 4, so if I go to the GIS map, so this is well number 4, okay? This is the same pipeline. If I double click here, this is the same pipeline that I saw in my GIS, in my network schematic. Here it is. It's the same pipeline, okay? So as you can see here, the GIS has the, what we call the GIS nodes. So if I go to format, right, I can show the GIS nodes. The GIS nodes are basically the nodes that I use to connect my pipeline or to define my 2D profile. Okay. These nodes are used, okay, while I am capturing the elevation. So for example, let me say that I will add now a new, let me just remove the GIS node now. And let me assume that I have another well here, and then I want to add another flow line to this, let's say, gathering manifold. So I'm going to, let's say, copy this well. So I will just go and say copy. And then I'm going to paste. So I have pasted the same well. Now what I will do is that I'm going to go to, as you can see, I have insert. So I can define any component in my check valve, etc., separator. Okay. I can now start clicking on my map, and each time I click, it will create a GIS node. So let me show you how I do that. So I'm now clicking many times, and then I'm now connecting with this junction here. So now I have added a new flow line. If I go to the format, I can view the GIS nodes that I created. As of now, if I double click here on this flow line, see, PIPESIM is not happy. It's complaining because I didn't enter the data. So when I double click here, now I need to enter the inside diameter. Let's say the inside diameter is 4 inches. But I still don't have the measured distance. I don't have the elevation. So I can remove the GIS. I can enter the data directly. Or if I leave the populate from GIS, with a click of a button, I go now to capture elevation. And now the magic will happen. So what will happen now? When I click on capture elevation, PIPESIM will go to the GIS, and then it will based on the latitude and the longitude from the GIS location, it knows the elevation. So it will populate the elevation automatically from the GIS. Isn't it awesome? Because in many oil and gas companies, pipeline surveys are sometimes difficult to find. Okay. So this is an excellent tool that help you build your pipeline networks automatically. Okay. So let me see, someone I think raised their hand. So let me just go to the chat. Okay, where's the chat? Where's the chat? Okay, I don't know. So let me see here. I think we're okay. So as you can see here, I managed now to capture the pipeline elevation from the GIS automatically, okay? Now, PIPESIM also is very powerful in terms of the heat transfer. You can go to the heat transfer, and then the heat transfer can be, you can either specify the heat transfer coefficient, or you can ask PIPESIM to do the calculation for you. And if that, you can define the pipe conductivity. You can define whether, you know, what is the pipe burial depth, if it's buried or not. And then also you can add coating for insulation. So you can define the thermal conductivity, okay, of the coating with its thickness. Let's say 0.5, 0.5, for example. And also I can define this coating, all right? Now, let's say the pipe is buried, let's say under maybe 5 inches. So as you can see here, the pipe is buried, right? And it is land, okay? It could be also subsea. Then I have other data for the heat transfer calculation, okay? So all that is useful. Now, let me just remove this pipeline that I've just added. And I can now go and run my network. But let me, before doing so, let me show you how I can actually build a new network, okay, using just the shape file, okay? So I'll just quickly do that. So if I go now to new network, don't save, okay? Now, if I go to the GIS, this is the GIS canvas. Now, as you can see, I'm on the world. I can easily zoom in to any area where I can build my network. I think my network is slow, or let me just do one thing here. Probably need to, okay. Is that better? I hope it's better now. So now I can click on import network. So let's assume that I do have the shapefile generated by the mapping team in my company. So click on import network. So I have this shapefile, for example. So this shapefile was created in an area in the US called Elmore. So when I click on open, now PIPESIM realized that this shapefile includes these attributes, we call it, pipeline properties. We have the PIPESIM inside diameter, PIPESIM wall thickness, but then I don't have any attribute. So that's why I'm going to override it with a value. So the default value is 0.5. Pipe roughness, I would like to look for any, do I have any attribute that corresponds to pipe roughness? No. Then I'm also going to override it. And now this is the environment data. And these are the flow line settings. Okay. Now when I click OK, see what happens now. So these pipelines with all its connections have been automatically constructed using the shapefile. And just to show you, if I double click here, so I have the inside diameter coming from the shapefile, but I still don't have the, you know, the measured distance and the elevation because I did not capture the elevation. So now I can easily go to Format, Capture Elevation. And now the elevations will be captured automatically from the GIS for all my pipelines at once. Imagine if you have, you know, a network of 200, 300 wells. Imagine the time saving that you will have here. Okay. Now I can add my wells. In the first seminar I did 2 weeks ago, which is PIPESIM Fundamentals #1, you can check also on YouTube. It's all available. I showed a recorded video for the same example where I used the same network and I built well models automatically from Excel using PIPESIM scripting. So I recommend that you go to that other recording and see how we did that. Okay. Now going back to the subject here, the network simulation, network modeling, and optimization. So if you go to help, you will find case studies, right? There are many case studies that are installed with PIPESIM when you install the software. One of them is called tutorials. And there is one tutorial that says network optimizer final. If you have access to PIPESIM software, you can easily play with that. And this is the network optimization model. And if you go to the help, this is a button here at the top right corner. You can go to the help, and then in the help, you can actually search for that. So you can easily go to the tutorials. And then the last example here, it says gas lift optimization study. And then it will help you step by step. There is a step-by-step guide on how to build the network with all the data, all the fluids, all right? And then the completions, gas lift data, completion data, etc. So all the wells. And then you can run the network simulation. Then there are also instructions on how to do the optimization. I recommend that you utilize this tutorial because unfortunately we don't have time really to go over this example and step by step. But this is the network. So now this is the final one. Let me show you what we have here. So in the network optimization, we had the maximum gas injection rate of 4, all right? So it was distributed among the wells. And let me just show you now the gas lift rate for each well. So what I will do now, this is a well. As you can see here, I double click on a well and then I open the well canvas. And you can see now the gas lift injection rate. It's 0.73, okay? So well number 1, we have 0.45. Well number 2, we have 0.95, etc. Okay? So now what I'm going to do, I'm going now to change this. I'm going to say that, okay, the gas injection rate for all of them is 2.5, for example. So I'm going to simulate that. So this is 2.5. let's assume that we are now over injecting gas lift, okay, in all the wells. Again, 2.5, and then finally 2.5. Now, if I run this network simulation against, let's say the sink pressure is, for example, 300. Now this is the network simulation now. I'm not running the optimization. I'm running the network simulation. So I will see that, so this is the sink, all right? This is the total liquid rate. This is the total water rate in the sink, right? So now, this is my sink here. So now, let us do some optimization, okay? How do I do that? Basically, number one, let's assume that I only have, right? Because right now I had defined my injection rate to be 2.5 for all the wells, which means that I am injecting 10 million standard cubic feet of gas per day of gas. Now let's assume that I need to reduce that. I need to say that my maximum gas lift rate that I have in the field is only 4. And then we will see how would that impact our oil production. So my current oil production is 1,660. So now I go to my network optimization. And now with the same boundary conditions, reset boundary conditions, now I'm going to say that my optimization control, I have maximum injection rate of 4, okay? And no local constraints. Now I run the optimizer. The first thing the optimizer will do is that it's going to generate the well curves, okay? And as I said, well curves will take a bit of long time, but once done, then next time it's gonna be fast, right? So WP or PWI is the well curves. Now it's playing with the you know, with the optimization, with the injection rate, because as I said, we have only 4, maximum of 4. So it's now trying to find the optimum gas injection rate, and it will see the impact on the production. As you can see here, it found that actually, you know, 4 is probably, you know, too much, because I can achieve the same with less gas injection rate. And this is what when I call we are over injecting. Now this is the optimization process. Now it's done. As you can see here, initially, what was my total injection rate? It was 10 million standard cubic feet of gas. And as you can see here, I managed to increase the total oil production by 1.9% with less gas injection rate, 3.9. See how this is powerful? Now, if I'm happy, see now the contribution, the distribution here. Initially, each well was receiving 2.5 million, and now I have managed to reduce that significantly. All right, and now if I'm happy with this, I can simply click on publish optimization results. Before I go to publish optimization results, let me just show you that my last network optimization, network simulation, I already ran that, and then this was my production per well, okay? And this was my the gas lift was high, and then I was producing total 1660, okay? And this is when each well was actually receiving, gas injection. So this is the gas lift injection. So each well was receiving 2.5 million. Now with the network optimization, I will manage to get the same, but with much less, and with these new gas lift rates. Now I will publish the optimization results, meaning I will send these rates back to my network. And now let me just make sure that I have done that. So I will go to the wells and then see, for example, here, well 1 was 0.07 only. So if I double click here now, and here we go. Now, with much less gas injection rate, I will run the network simulation now, not the network optimization, because I have optimized my network. Run it. And now my network is optimized, okay? And this is my, as you can see here, if I go to the sink, this is my new production, all right? And my gas injection is much less. So this is the beauty of production network optimization. And this is same example applies to ESP, it applies to chokes. I can easily, distribute the choke settings into all my field at the same time. So I believe with that, I'm done. So we can open the floor to any questions if you have. Let's go to the chat window. So we have a question here. So the number of nodes, if I am in the GIS, canvas, all right, if there is a straight line, you just need to put two GIS nodes. If there is a deviation on the 2D, you need to put nodes, basically, because between two nodes, it's going to be a straight line. Okay, so it really depends on the curvature, the 2D curvature, okay? Confirm if economics has a role to play here with a 1.5 oil increase by activating gas lift. Does it justify the cost of gas lift infrastructure to be installed in the field? Well, by the way, 1.5, this is based on the configuration that I put. But as you said, we have to always look into the economics, right? So for example, let me just show you here. Let's assume that, so this is my my wells, okay? This is my, so my network simulation, all right? What if I remove the gas lift? What will happen, right? So let us see, if I go now to my wells, and then I can deactivate the gas lift valve, okay? Assuming that I will not run the gas lift. So just to see if, as you said, if this is a good justification. So what I can do is I can right click. No, I will not delete. So I'll just say that it's not active. Okay. So this is for well number 1. Well number 2. This is not active. Well number 3. This is not active. And then well number 4. This is not active. Okay. So I have now deactivated all the gas lifts. Now I go to my network simulation. So remember, I was producing, let me just go to only the sink. I was producing 1,658. So now if I run now, after I deactivated my gas lifts, no solution possible. So my wells are actually not going to flow. See, this is an indication of, and also I can look into the wells, for example. So let's say if I reduce the sink pressure, will the wells start to flow? Let me see. It is still struggling. So as you can see here, the gas lift is actually, important for the wells to flow. So now when I reduced the sink pressure, then I start to gain some production. Okay, but I had to reduce the sink pressure. Okay, now let's assume that, let's see, okay, if I now open the gas lift, what will happen to my production? Right now it's 1461, right? So now if I go to my wells and then start to activate the gas lift for the same now gas pressure or same sink pressure, what will happen? So activate this guy, activate this guy. Now I have added the gas lift again to my wells. And now remember, this is 1461. Now I have 2000. See? So that's a major increase. Okay. So if the well did not flow without artificial lift, then how did we arrive at the 1.5? So no, remember initially when I ran the network, I ran it with 2.5. Okay. So we were over injecting, and as a matter of fact, by reducing the gas lift rate, we were able to increase the oil production. You see my point? So when I did the optimization, I was actually able to increase my oil production by 1.5 by reducing the gas lift rate. Is this clear, Joseph? So initially, when I had my network, I used to put 2.5 million in each well, and I was over injecting, and the gas lift rate was too much that will make even the wells worse. So the optimizer reduced the gas lift rate and increased. So 1.5 is actually compared with 2.5. It's not without anything, right? So any more questions? Yeah, you're welcome, Joseph. Yeah, any more questions? How could we output the results report as PDF? Well, PDF, we don't have PDF, but you can have the same, like for example, this is a data grid, right? So you can easily copy, Control C, right? And then you can put it in Excel if you want. Like this, okay? And by the way, you can go to each, if I expand, for example, any equipment, you can go to the, let's say this is a completion, so you can look into the downhole conditions. You can go to the gas lift, and then you can go to the profile results where you can select any well and look into the pressure profile individually. So this is, I mean, so we have node results. So if you go to, for example, to CPF, which is the sink, this is the sink, right? So you can basically copy and paste it outside. We don't have this. I mean, we feel that it's really straightforward to just copy and paste it in Excel or anything. But maybe you can consider exporting to PDF. The thing is, it's difficult to find a format that will please all clients. So we believe that, you know, you can create your own format by just copying and pasting, and you can add or remove, you know, any columns from this grid if you want to define your own output, right? By the way, export here is not exporting the results. This is exporting the engine keyword file. This is for us. It's an advanced option that I activated. Usually you don't see this. This is the output details in text format. This is the output summary. You can take that and put it, you know, in Excel, for example, and so on, or Notepad for that matter. And you can also, you know, if you have any pipeline that you'd like to see the profile results, you can show the plot for the profile, and you can select multiple, you know, pipelines and compare, you know, the profiles in one plot. Okay. You can also, you know, basically take a screenshot here and paste it somewhere. Any more questions? If no more questions, I'd like to thank everyone. Thank you all for attending this this last session. You know, please reach out if you have any special question. I'll be more than happy to